Hi everyone, it is absolutely a privilege for me to participate in this ICCIC 2021 conference. I will be talking about mitigation of RSSI variations using frequency analysis and command filtering. Our paper ID is 150. Before that, let me introduce myself. My name is Shilpa Shaju, working in Muthoot Institute of Technology and Science. My co-authors are Dr. Arun Gandhi-Jose and Mr. Rishikesh P.H., both working in Muthoot Institute of Technology and Science. This work is a part of GST-funded project. This will be the content we will be going through: the introduction, literature review, objective, preliminary study focusing on RSSI and RSSI filtering, system design, experiment and analysis with the subsection of setup for experiments, RSSI fluctuations, analysis of various filters. After that, we'll be looking into the conclusion and features graph, acknowledgement, and finally the reference. So let's start with the introduction. The use of smartphone makes the people to complete their daily tasks in a faster and easier manner. One of such tasks is the navigation. GPS is used efficiently in the outdoor navigation but fails in indoor navigation. People demand smartphone-assisted indoor navigation solutions. For the indoor navigation, we are using different technologies and techniques: wireless fidelity, Bluetooth, especially Bluetooth low energy, ultra-wideband, acoustic signals, ultrasound, radio frequency identification are some of the technologies. RSSI, or Received Signal Strength Indicator, angle of arrival, time of flight, and time difference of arrival are some of the indoor navigation techniques. By combining these techniques and technologies, we will get a better solution which will enhance the precision, reliability, and reduce the computation complexity as well as the energy consumption. So RSSI is a widely used indoor navigation, but the problem with this RSSI is that the values is always fluctuating due to different environmental factors, barriers and noises. So it is important to reduce the fluctuation by using various filters. In this work, we are using a new filtering method based on the combination of frequency analysis and Kalman filtering. In the background research, we found that different wireless devices have the built-in RSSI circuit, and hence there is no need of any additional hardware. The RSSI method is mainly used to calculate the distance between transmitter and the receiver. But the problem with the RSSI system is that the values are always fluctuating because of different environmental factors. We are giving the footnotes of different references. Another filter is a span thresholding filter, which will lessen the fluctuation, but its performance is degraded if the test area is filled with human. Weighted average, exponential, smoothing filtering, wavelet filtering, least mean square filtering are some of the other filters. But this filter does not give a better solution, and the study showed that the combination of these filters will give a better solution, but it is limited to exterior environment. Indoor navigation systems are using Kalman filtering, and sometimes this Kalman filtering is used with a beacon to improve the accuracy, but it is mainly suited for the large indoor areas. And another type of filtering is this Kalman filtering is applied along with the beacon rate algorithm, and the result shows it improved the result up to a few centimeters. Coming to the objective. The objectives of our work are to study about the fluctuations in RSSI, to design a custom filtering method to remove the fluctuations in RSSI, and to analyze and compare different RSSI filtering methods. So this is the preliminary study. about RSSI. RSSI, or the received signal strength indicator, indicates the power of the received radio signal and its unit is dBm. RSSI is a free input to the system and hence cost effective. As we said earlier, there is no additional hardware required. And the RSSI values received by the Android phone fluctuates in time. These are some of the filtering methods. The mean filtering, where we are calculating the mean of the collected RSSI values. But the problem with the mean filtering is that if the fluctuation number is allowed in the received RSSI, then the result suffers. Coming to the median filtering, we will arrange the different received RSSI value in a sorted form and we will find the middle position value. The next one, it is the maximum filtering. In the maximum filtering, we are choosing the maximum RSSI value. If the greatest value is the fluctuation value, then the result again. So the next is the RSSI filtering method known as Kalman filtering. So this is a mathematical linear optimal state estimation method. It is predicting the future state of a system based on the previous state. In a Kalman filtering, there are two steps: prediction and update. Another one, it is a frequency analysis filtering, where we count the number of times an RSSI value will appear. So if that number is greater than or equal to a predefined threshold value, we will accept that RSSI, or if it is less, we will reject that value. So let's discuss our system design. This is a block diagram of Kalman frequency filtering. So first we collect the RSSI values and then we apply the Kalman filtering. After the application of Kalman filtering, we find out the frequency count of each RSSI and we set the predefined threshold value as 15%. So if the frequency count is greater than 50%, we save that value, otherwise we reject the value. And we named this as the Kalman frequency filtering. Another one is that we collect the RSSI values, then we find the frequency count. And after that, if the frequency count is greater than 50%, we accept the value, otherwise we reject the value. And we apply the Kalman filter for those selected values and save the value. So this is named as frequency Kalman filtering. So let's look into the result section. So we choose the test bed as the laboratory room of Ramanujan block of Muthoot Institute of Technology and Science. We place the reference node, that is the BLE node, in the fixed position, and we place the RSSI receiver. In our case, we choose it is the Android phone, and these are placed in line of sight with the BLE device, and they both are in the same height. Then we collect the RSSI value using an Android phone at different distance with a scanning interval of 2 seconds, and the different distance we used in our experiments are 1 meter, 2 meter, 3 meter till 6 meter. And we choose two test cases. One test case is from 10:30 a.m. to 11:30 a.m. and another test case is that from 3:30 p.m. to 4:30 p.m. So this is our first result on RSSI fluctuation. We collected RSSI value at same position at different time, and we found that we get different number of samples in each scanning. So we done 6 scanning and each scanning interval is said to be 2 seconds, but the number of values received in each scan is different. This is the result of our test case 1, and the graph is plotted using the standard deviation. So we assume the standard deviation is the measure of noise. So you can see in the figure we are getting the values for each filter at 1 meter, 2 meter, 3, 4, 5 and 6 meters. So the blue vertical bar indicates that we are applying no filter, red for frequency analysis filter, yellow for Kalman filter, green for frequency Kalman filter, and orange for Kalman frequency filter. And we found that that green vertical bar, that is the frequency Kalman filter, have the less height, which means that it is having the less standard deviation in test case 1. And this is the result of test case 2. As we said earlier, it is of 1 meter, 2 meter, 3 meter, 4 meter, 5 meter, 6 meter data collection. And here also the green vertical bar for frequency Kalman filter is the lowest comparing to other filters. And thus we can conclude that the frequency Kalman filter is the better filter comparing with others in terms of standard deviation. And this is the conclusion and future scope. So the raw RSSI signals are filtered using different filtering methods, and thus the fluctuations can be reduced. And among different filters, frequency Kalman filter was found to be the best based on the standard deviation values. And we found some challenges during our work, that is during scanning for a fixed time interval to record the RSSI values. The number of samples received was not consistent, and of course the RSSI fluctuations. And in the future we are aimed at considering with the real-time environmental factor with multiple BLE devices. This is area where we are going to acknowledge the DST and the effort of our institute management and the officials. So these are